So this is ECE 343 Signals and Systems, the fourth lecture for Chapter 1. Previously, we had gone through an introduction to systems, including looking at a variety of system properties. This lecture is just going to finish out Chapter 1, wrap up some loose ends, and get us ready to move to the next chapter, which is the solution of constant coefficient linear differential equations. The first loose end that we'd really want to deal with is introducing something called operator notation. So operator notation just is one of these compact operator notation. It's a compact way of helping us describe systems or describe mathematical operations. Many of you have seen this before. I'm going to introduce this from the context of the derivative operator, and it's something that we're going to see multiple times in this class. We'll use operator notation for derivatives, for example. We'll also use it when we move to discrete time type operations, when we do a system delay. So what is operator notation? Operator notation really just utilizes some symbol to designate an operation. So you could think of something like a derivative, right? A derivative. You've seen a derivative before, something along the lines of d dt of x of t, and that gets to be just a little bit cumbersome to write out all of the time. And so what we might do is we might go ahead and think about that operator d dt, and we're going to come up with a notation for that operator that's just a little more compact. We're going to go ahead and adopt just a capital letter D to indicate that derivative. So if I write out something like d, right, xt, what that really means is this first order derivative d dt of x of t. You've probably seen some other type of operator notations for derivatives. D dt of x of t, you probably have also seen stuff like this. You've seen it like with a dot notation, so x dot, that's a form of operator notation in a way. It's a shorthand. You might have also seen it something like this, where you had like a prime symbol, so an x prime of t is sometimes used to indicate a derivative. You might have even seen another one that has like a parenthetical. We might have used that when we introduced Taylor series, so an x parenthesis 1 of t would be the first order derivative of x with respect to t. All of these are indications of derivative, but for us, this operator notation is just going to be replacing this derivative with a letter. And we're going to do it in such a way, or we're going to allow this notation to be such that we can do things like multiple operations, like taking repeated derivatives, just by repeatedly applying that d. And we're going to adopt a notation that looks a little bit like a polynomial expansion. So for example, if I went ahead and I did a d squared dt squared, right? In calculus, what does this mean? This means I'm going to take the derivative of some signal x of t. So I guess if I was going to be complete here, I would have put an x on there, something that this guy's acting on. We said that we were going to use an operator notation, so we could get a d here, and we're going to have another d and an x of t. And just because of its natural appearance of something that almost looks like multiplication, we can go ahead and just designate this as a d squared x of t. So a d squared would just indicate a second order derivative, or a derivative followed by another derivative operation. Even though this looks like a polynomial, a d squared, we do have to be careful in the time domain of treating it like a polynomial. We'll talk more about this later. Part of the reason we continue with this particular notation is that we're going to see it has a tight connection to actual polynomial or actual multiplication when we introduce this idea of transform domain analysis. For those of you who remember a little bit from your circuits class, going back to something like a Laplace transform of a differential equation, one reason that that is so powerful is because a differential equation, hard to solve in the time domain, under a Laplace transform becomes much easier. It becomes an algebraic equation. Derivatives become just some form of multiplication. We'll see that when we get back to or get to the topic of Laplace transforms. So this idea of operator notation, we're going to substitute an operation with some convenient letter, and we are going to allow for the cascade of these operations just by taking that letter raised to some power, right? You can think of it as looking like it's raised to some power to indicate repeated application of those derivatives. So a d squared would be a second derivative. If I did something like a d to the n, right, that would just be the nth derivative with respect to time. So it's an nth order derivative, something along those lines. To maybe get an idea of how this is used or applied to the topics of signals, let's go ahead and take a look at an example from circuits, I'm going to go ahead and try to draw out a electric circuit, and we'll start thinking about how we might take a look at this guy. So in this particular example, let's go ahead and draw out a voltage source. So I'm going to put in here a voltage source. I'm going to call that voltage source f of t, something along those lines. I'm going to then have that voltage source go through a resistor. So I'll go ahead and put that resistor in there. I'm going to allow that resistor to be 2 ohms. So I'll have a 2 ohm resistor. And then I'm going to have that path continue, and it's going to go through an inductor. And I'm going to go ahead and allow that to be a 2 Henry inductor. And then there's going to be a branch point here, so I'll put a little node symbol. One of the branches of the node is going to continue to another inductor, so I'll go ahead and throw that other inductor in there. I'm going to go ahead and let that be 1 Henry. And then that 1 Henry inductor will go into another resistor. And that particular resistor, I'm going to let it be 4 ohms, something along those lines. And then from that middle node that we hadn't quite dealt with, I'm going to go ahead and let that go into a resistor as well. And so I'm going to let that be a 3 ohm resistor. And then I'm going to just close out all of these loops. So I have got a little circuit that everybody should be familiar with. You've seen this sort of stuff back in your circuit analysis days. You've been able to see these guys as a type of circuit that you should be very comfortable with in both modeling and solving. I haven't yet designated any kind of output variable. I'm going to go ahead and allow myself 2 output variables here. This is typical of how we'd maybe approach an analysis of this guy anyway. So I'm going to go ahead and take a look at this first loop current, and I'm going to let that be one of my output variables. I'll call that guy Y1, and I'll look at the second loop current, and I'll call that guy Y2 of t, something along those lines. So now I've got a complete circuit. This circuit is reflective of a system. It's a system made up of resistors and inductors. It has an input, that's a voltage source f of t, and it's also got an output. In this case, there's actually a couple of outputs we could consider. A y1 of t, the first loop current, and then a y2 of t, the second loop current, something along those lines. I would like to go ahead and set up the equations or the math so that I can look at this guy. And I'm going to start it by thinking about ideal inductors. So we know from circuits that an inductor is a device, right? An inductor is a device that has a very particular voltage current relationship, and that voltage current relationship looks something like this. The voltage across the inductor, right, is equal to the inductance times the time derivative of the current through the inductor. And so I'm going to go ahead and show this using operator notation. So I have something like, I guess if I was going to be really complete here, I might do something like this. I might say the voltage of the inductor as a function of time is equal to the inductance times the time derivative of the current through the inductor as a function of time. This is ideal inductor behavior expressed using operator notation. So I've got to start on this guy. I've used my ideal inductor knowledge, and now I want to go ahead and write some equations that will help me describe the input-output behavior of this system. You've done this in circuit as well. What I'm going to do is I'm going to do some loop equations here. I'm just going to look at the voltages around a loop. They have to all sum up to be 0. This is Kirchhoff's voltage law, and so KVL. And we can start with this first loop in here. So if I take a look at this first loop, right, we see a voltage source f of t. That's the only source that's in there, and we know that that voltage has to be equal to the sum of all the voltages across the components that is part of that loop. So the first voltage drop there is going to be the resistance times the current. So I'm going to get something like a 2 times y1 of t, because the current is y1, resistance is 2. That gives me a voltage then. The next one would be the voltage drop across that inductor, but we already know what that looks like. That looks like what? It's the inductance times the time derivative of the current through that inductor, but the current through that inductor is y1, so I'm going to get a plus, right? And I'm going to get 2 d y1 of t, something along those lines. And then the last thing I'm going to get in that loop is I'm going to get the voltage drop across that resistor. In this case, though, I have to take a difference of currents, right? I've got the current that's associated with y1 going in the direction top to bottom in my picture, but I've also got that back current, right, from y2 going bottom to top. So the net current through that resistor is going to be y1 minus y2. So if I get that last voltage in here, I'm going to get the resistance resistance, 3, right, times the net current going through that, which is y1 of t minus y2 of t. So that's KVL at the first loop of this circuit. I have a single equation, right? One input, but two outputs. So that's a little dissatisfying. Usually we like to think of an expression that gives us a relationship between an input and a output, like y1 or y2. And right now we've got a mix of y1 and y2 in there. Well, the second loop equation should help me with that. There is no independent voltage source in there, so there's no a term that we have to worry about on the left-hand side. That's just going to be 0. And we have to sum up all the voltage drops across those components. They have to all sum to 0. The first one I might do is the voltage drop across that 3 ohm resistor. So I'm going to have 3. And what's the voltage as I make my way around that loop in the direction of y2? Well, the net voltage in there, right, is going to be taking something like y2 minus 1. So I'm going to have 3 times y2 of t minus y1 of t. That gives me the voltage drop going around in the direction of y2 in there. Then I'm going to go across that 1 Henry inductor. That's very much like what we had seen before for the other loop, except for now it's an inductance of 1, right? And we're going to be talking the derivative acting on not y1, but is the current of the second loop, which is y2 of t. And then the final drop on this one is going to be that current going across that 4 ohm resistance. And so I'm going to have something like a plus 4 y2 of t. So again, we get an equation. This one has just our output variables y1 and y2. Two equations, right, helping us describe the behaviors of the system. Normally, like I said, we'd want to be able to find a single expression that has input and one of the outputs, either y1 or y2. So we can certainly think about how we might do that. The way I'm going to do it is I'm going to work with these two expressions in operator notation, and I'm going to collect terms together. So let's call this first guy equation 1 and the second one equation 2. And what I'm going to do is I'm going to be working with equation 1. So equation 1 has f of t being equal to, and let's get all of those things associated with y1. There's 2y1 plus 3y1. That's a total of 5y1, right? So we're going to have something like 5y1. And there's also a 2 derivative y1. So I'm going to write that as a 2 derivative plus 5, that whole thing acting on y1 of t. And actually, that's probably a more appropriate way of describing this particular operation, right? This operator notation, right, isn't like a polynomial multiplication, but it is an operation of that operator on the target, in this case, y1. So 2d plus 5 is 2 times the derivative acting on y1 plus 5 times y1. And if you look at all those terms, they're what we originally found in our expression. So we had a 2dy1, that's this piece, right? That's this 2d acting on y1. We also had a 2y1 plus 3y1. That was plus 5y1, so that is the second piece in there. So we got all of those guys in there, and we just need to add in now the second term, which is only to do with y2. So this is just getting things separated out a little bit so I can see where the y1 pieces are and where the y2 pieces are, and an operator notation helps facilitate that. The last one then is that minus 3y2 of t. So completely equivalent expression. I've just collected terms, and that collection of terms is going to help facilitate trying to use these two equations to come up with a single equation. I'm going to do that now for equation 2, same sort of an idea. I'm going to get a 0 on the left, and then I'm going to collect all the things to do with y1. In this particular case, I'm going to have a minus 3y1 of t, right? And then the second one has what? It has a derivative acting on y2, and then I had like 3y2 plus 4y2, that's going to be 7. So a derivative plus 7 acting on y2 of t. Completely equivalent expression to that first or that second equation that we got from Kirchhoff's voltage law on the second loop. So this pair of equations, again, completely equivalent to what we had before, just in a little bit more convenient form. What have I got as an operation that I want to do? I would like to get maybe an expression that has just f. So what do I seek? I want one expression with only, right, the input f and the output, well, let's just take it for right now, y1 of t. right? And so in other words, I don't want no y2. I don't want to see y2 in this guy. So how can I do that? Really, the game here is to combine these two expressions in such a way that the y2 terms cancel. One way that you can think about that, these equations are equations, and I can operate on the equation with things like derivatives and additions and any linear combination of derivatives and sums of constants. I can operate on these equations without changing the equality. So let's take a quick look at this guy. I have an expression, the first one, right? And it's f equals 2d plus 5 acting on y1 minus 3 acting on y2. The second expression is 0 equaling minus 3 acting on y1 plus d plus 7 acting on y2. I would like to get an expression that only has y1s and gets rid of all the y2s. So what I can notice here is the first expression has a minus 3y2. The second expression has a d plus 7y2. If I took this first expression, right, and operated on it with a d plus 7 operator, then the thing that would be operating on y2 would be minus 3 times d plus 7 operating on y2. And in the same way, if I took the second expression and operated on it by 3, I would get a 3d plus 7 operating on y2. And then if I added those two equations, adding equations together doesn't change their equality. The term that's operating on y2 from the upper expression would completely cancel from the expression acting on y2 on the lower one. So let's go ahead and do that. Let's go ahead and run out the math on that. So I'm going to have what? I'm going to have d plus 7 acting on that whole equation. So on the left-hand side, I'm going to get d plus 7 acting on f of t, right? And then I'm going to get d plus 7 acting on 2d plus 5, right? Acting on y1 of t, right? And I'm going to have a minus 3d plus 7 acting on y2 of t. Haven't changed, right, the equality there. I've just operated on it. Taking the derivative of an equation doesn't change the fact that it's still an equality. Multiplying an equation by 7, both sides left and right by 7, doesn't change it. Adding those pieces together, those equations together, doesn't change the equality. So this is just a modified form of 1. Let's call it 1 prime, something along those lines. Doing that second operation that I saw in the second one, so this is a modified version of the second equation. I'm going to get 3 acting on 0. That's still 0, right, being equal to. And then I'm going to have minus 3 and 3. That's going to be a minus. Whoops. Let's get this thing to cooperate. So we are going to get in there a 3 times minus 3. That's going to be a minus 9. A minus 9. I have no idea. Let's get this guy, hopefully. There we go. So 0 equals minus 9 acting on x1 of t. And then I have what? A 3d plus 7. So I'm going to have a plus 3 acting on d plus 7 acting on y2 of t. What do I notice here now? I notice that this first expression has a minus 3d plus 7y2. The lower expression has a 3d plus 7y2. If I add, right, equation 1 to equation 2, adding equations doesn't change the equality, right? What I notice is that I completely eliminate the y2 term, which is exactly what I wanted to do. You probably did some variant of this in circuits. You might not have seen it in this way. I personally think the operator notation is convenient for trying to figure out how to solve these equations for a single input, single output as an example. So what do I get on this? I'm going to get something like a d plus 7 acting on f of t, the input, right, is being equal to. Let's expand out that set of operators. I know that the derivative acting on 2 times the derivative is just 2 second derivative, right? So I'm going to get a 2d squared. There's a 14d and another 5d. Add those guys all together, right? We should get a 19d, something like that. No problem with doing this. And then I'm going to get a 5 and a 7. That's going to be plus 35, right? Oh, but when I add that second equation in there, I'm going to get a 35 minus 9. And that whole thing is going to be acting on x. Wow, I don't know where that x came from, so let's go and correct that. That should have been y, right? We had an output on there, so we must have had that quirk come out when I was having problems before. So y1 of t, something along those lines. do a little final cleanup on this. Convention on differential equations would be to go ahead and have that output term on the left-hand side. And so I'm going to show this as a 2d squared, right, plus 19d. And I'm going to have 35 minus 9 is gonna be a 26 on there, so I'll have a plus 26 acting on my output variable of interest, y1 of t, being equal to a d plus 7 f of t. So single input f, single output of consideration y, and a differential equation description relating the behavior of input to output. That was the thing that I sought. A couple of comments on this. I guess if I was going to be 100% picky and really make this truly a standard form, that lead coefficient for the d squared, the highest order of the derivative on y, I probably want it to be 1, so I would divide the whole expression by 1/2. I'm not going to worry about that here. That's just something that's easy to do, multiply the whole expression by 1/2. The second thing that I would note, and this one is probably worth emphasizing, take a look at that derivative operator acting on my output variable y. This is a second order differential equation description, right? So the circuit resulted in a second order differential equation description that related the input F, a voltage source, to the output current Y. And the highest order of derivatives we see there is 2. Go back to the original circuit and we can ask the question, does a second order differential equation description seem to be consistent with the circuit that I see here? And what I hope is that everybody from circuits realizes that when you see an energy storage element like an inductor, that inductor contributes a derivative, right? It contributes a derivative to the differential equation. So here I have a circuit with 2 inductors. There's one inductor, there's a second inductor. Because there's 2 energy storage elements, there's going to be 2 initial conditions that this circuit can support. There's 2 degrees of freedom. There's 2 memory elements, if you will. Inductors are a form of memory, is one way of thinking about them. That 2 elements that can store energy is going to correspond to a second order differential equation. You can do that as a very quick check. If you had ended up with a differential equation that was like third order, you might know that you have to go back and take a look at it because there weren't 3 storage elements in there. So second order system from a circuit that has 2 energy storage elements, that looks good. So we can go back in here and we see we get that second order differential equation. The other thing that I would point out is that there's other ways of us getting this expression, right? There's other ways of getting this expression. So let's say an alternate way to get this result, Okay, we could go back to those expressions that I had previously, the equation 1 prime and the equation 2 prime, and I can take EQs, right, 1 prime and 2 prime, something like that, and I'm going to express using kind of a matrix representation. Okay, so let's go ahead and take a look at what that might look like. I had, if you look back at that first one, and actually I didn't have to do it for even 1 prime and 2 prime. I could go back, and probably this is easier. Who wants to go through all of that? Let's modify this a little bit. Let's just use our original equations that we got from KVL. So let's use equations 1 and 2. Let's get rid of those primes. Let's really save ourselves a little bit of effort here. So use the originals in there, and if I look at that original equation, right, and I collect all those terms that I had seen in here, and I'll do this in green, I had 2d plus 5 acting on y1 and minus 3 acting on y2. So matrix style, I could have done something like this. I could have done 2d plus 5, right? And that's going to be acting on y1 of t. And then I had in there a minus 3 acting on y2 of t. And this whole thing has to be able to give me, well, the other side of that equation, which is the input f of t, something like that. So as I've written it right now, I've just captured the equation 1 as part of a matrix representation. If I go back to equation 2 in there, I had 0 equals minus 3 acting on y1 and then d plus 7 acting on y2. So I should have a minus 3 in here and a d plus 7. Those are going to be acting on y1 and y2 respectively, and they give gives us a 0 on the other side. So this is just a matrix representation. This is a matrix representation, right? With operator notation, operator notation, right? So it makes this nice compact form on that. This is a matrix representation of our system equations, right? System equation. And what do we know about a matrix representation of things? This first part, right, is kind of like a matrix A acting on some output vector Y being equal to something else. Let's just call that, some other vector B. If I want to solve for Y, right, I can do that matrix style. So I can solve, right, for y1 of t using matrix approaches. Like Cramer's rule, right? We just talked about Cramer's rule earlier in part of our background math chapter. So you can do things like apply Cramer's rule to this, and you can end up getting an expression that would give you the same equation. Basically, what you'll get in that case is you would get something that would look a bit like this. If you did Cramer's rule on that first one, you'd get something like a y1 of t equal, and we have to be just a little bit careful on here because it's going to look a little bit weird. You're going to have that d plus 7, f of t, and then because you divide by the determinant of that a, that determinant of a is going to be that 2d squared. I'll let you work out the details on that. That 2d squared plus 19d plus 26. Okay, so Cramer's rule would give you something like that. We know this division by that doesn't really make much sense, so just operate both sides on this, and so, or you can cross multiply, and we'd get a 2d squared plus 19d plus 26 y1 of t being equal to a d plus 7 f of t, exactly the same. So we get exactly the same response or result in there. This denominator part, right, this part in here that came out of Cramer's rule, right, that came out of something like determinant of A. We can still do that even though it has the operator notation in there. Let's just go ahead and do that for fun in this particular case. Here was my A, right? If I wanted determinant of A on that, what would I do? I'd multiply the main diagonal elements, right, or have one operate on the other. That'd be a 2d plus 5, right? And then I'd have a d plus 7, and then I'd subtract the products of the off diagonal, that backwards diagonal. Minus 3 times minus 3 is 9, and with another minus sign, I'd get a minus 9. Do that all together, I'm going to get a 2d squared, I'm going to have a 19d, and I'm going to have a 26 in there, exactly like we would have expected. Here's another thing to note. If I wanted to go through and solve for y2, I could also do that with Cramer's. And what do you know is going to be in the denominator? It's still based on that determinant of A. So you know already that that's going to be a 2d squared plus 19d plus 26 in there. And if you go through the other part of the math and you do the other one, what you get here is basically a 3f of t. So if I solve that guy, I would have gotten a 2d squared plus 19d plus 26 acting on y2 of t being equal to 3. Whoops, that should have been a 3. So we'll go ahead and make this guy a 3 times f of t, my input. Okay, that's another equation. That's a single equation that relates input f to the second loop current, y2. Also a second order equation because it comes from a circuit with two energy storage elements, right? And something to note here, they both have that same polynomial, right? That same operator acting on the output variable. This turns out not to be accidental. It happens every single time. It's something that I hope you have seen before in circuits class. This thing right here has a particular meaning or connection to the system itself. So the first thing I'm going to note here is that these guys are the same. And why are they the same? They're the same. They are the same, right? Because both y1 and y2, right, share the same underlying circuit. So this is just another one of those ones that can allow you to do some quick checks on your math. If you're looking at some circuit that's made up of resistors, capacitors, and inductors, let's say there were 3 inductors and 2 capacitors and 12 resistors. 3 inductors, 2 capacitors, so that's a total of 5 energy storage elements. After you do whatever kind of analysis you do, you should get a 5th order differential equation. If you didn't get a 5th order differential equation, you know something's wrong, you know you messed up somewhere, and you need to go and check it out. The other thing that you should be able to do is you should be able to take a look at all the different outputs that might be on there. There could be many different outputs. And if you wrote the input-output equation through a differential equation, that polynomial operator that's acting on whatever output it is that you are interested in had better be the same for every single output that is a part of that circuit, because every single one of those outputs shares the same underlying circuit. We'll find out later that this particular term out front is something called the characteristic polynomial, and it's called a characteristic polynomial because it tells us something about the character of the system. And that operator notation, which is how we started down this path anyway, really gives us a convenient way of working with that. So we're going to see operator notation come up a lot, and it's going to have a tight connection with what we see form-wise when we do things like a Laplace transform. Okay, so let's switch gears just a little bit, and let's take a look at this idea of an internal versus an external description. Internal versus external descriptions. Oops, some descriptions. What I would suggest here is that you definitely make sure you're reading along in the book. The book does a nice job of these topics. I'm not going to overdo this too much. An internal description and an external description are just different ways that we might view a system. Let me try to demonstrate this with an example. Basically, the idea between, or the difference between these are, an external description is a way of understanding a system or a way of looking at a system that only allows you access to the input port and looking at what kind of outputs are generated. So in other words, I might have some system. I'm going to go ahead and draw this system in here, and I'm going to put a cover over that system so you can't see what's inside of it. But I do have an input port where you have an input x of t, and you have an output port where you get an output y of t. And we say, okay, what does that system do? What does the system do? What is the system function, right? The system function, behavior, whatever you want to do. What is the system function? What does it do? Okay. Because I can't see inside the box, right? I'm really constrained in this particular instance to understand system behavior by applying some input, seeing what comes out, apply a different input, see what comes out. And based on those input-output behaviors that I see, trying to get some understanding of the system behavior. That is my external description. So if I learn that, if I try to figure that out, if I figure it out, you know, if I just use x going to y's to answer this, you know, the system function, right? Just based on input output stuff, that is my external description. Okay. So I might do something like this. I might sit there and say, okay, I'm going to apply a bunch of sinusoids to this. I'm going to put in DC first, and I find out it passes DC. I'm going to put in 100 hertz, and I find out it passes that 100 hertz exactly the same. I put in 200 hertz, and it passes that 200 hertz. And then I put in 300 hertz, and I find out the output goes to 0. And any frequency after 300 hertz, it goes to 0. What I might begin to infer then is what? That this is a low-pass filter, and it's a low-pass filter with a cutoff frequency of 300 hertz. I sat there and probed the input, right, with a bunch of signals, and I choose my signals in a smart way to help understand system behavior. I think we can all recognize that this external description is a little bit limiting, right? There are things that can go on inside that box that are hard to tell just by probing it with an input and looking at what is the output. In fact, there's a whole class of behaviors that might be impossible to see. The book talks about this idea of observable and controllable systems. Get that a read. That has something to do with those systems that can have some sort of hidden behaviors from an external description. External descriptions are a little more awkward, and they might not be 100% complete. So what could I do instead on that? I could instead go ahead and take a look at that system, right? And I could pull the cover off. So I'm going to take that cover off. cover off, right? Cover off. It's no longer a black box. Sometimes you'll hear this notation that a system might just be a black box. That black box kind of an idea for a system is that you've got a cover on there, you can't see it. I pull that cover off, and now all of a sudden I might see something like this. I might be able to go inside that circuit and see, right, that there is a resistor and a capacitor like this, X and Y. And because now that I see the components in there, I can apply circuit knowledge, my circuit knowledge on that. So I can do circuits onto this circuits and get, this nice differential. I could get this nice differential equation, and I can figure out a relationship between input and output. I could still find in this particular case, right, I've got an R and a C in here. This is a low pass filter, and if I know the value of R and I know the value of C, I can figure out where the cutoff frequency is in that. So I can still verify that this was a low pass filter. I just can do it in a much more precise way, in a much more methodical way, and a much more transparent and complete way, if given the choice. So this whole thing is what? This is an internal description. That internal description, right, helps me better see what's going on inside because I can see inside. That internal description is generally preferred. So we generally prefer an internal description, right? It can be easier, more complete. Both of those can happen in there. We don't always get it. Sometimes we are only given access to a system that you can't, pull the cover off of, if you want to think of it that way. And so sometimes we have to be satisfied with an external description. An example of this might be in communications. If I have a satellite in space and it transmits a signal, right, to Earth, and you've got a receiver on Earth, what is the system there? The system is this very complex, system that is the atmosphere of the planet and all the other kinds of things that are going on in that atmosphere, mountains and other things that might cause some signal distortion. It's this incredibly complex system for which you're never going to be able to fully know an internal description on that. So instead, we almost always in that case would content ourselves with an external description, taking looks at how different inputs generate different outputs to help us model or understand that system behavior. There's a nice book example. I'm going to just briefly do this. I'm not going to go through all the circuit analysis. You can take a look at that in the book. So there's a voltage source here, F, and I'm going to let it go through a resistor 2, and then it's going to go into another one, 2, and there's going to be another resistor in there too, and then I'm going to have a 1 ohm resistor and a 1 ohm resistor and a 1 ohm resistor and a 1 ohm resistor, and I'm going to tie these guys together, something like that. And then I'm going to put a little capacitor, a 1 farad capacitor in between there. And I'm going to go ahead and look at the voltage across that 1 ohm resistor, and I'm going to call that V of t. Okay, if you go ahead and you analyze this guy, what you end up getting from a circuit analysis, looking at the external, looking at the internal workings of the system, looking at all those circuit connections, is you get something like this. You get an 8 2D plus 1 acting on V equaling 2D plus 1 acting on F, something like that. You get a first order differential equation, right? Which makes sense. There's one energy storage element in there. There's a capacitor in there. So there is something satisfying about this description for this system. It does let us know something about input-output relationship through a first order differential equation. Notice something though here. There's the same operator on both sides, 2D plus 1 and 2D plus 1. Let's talk a little bit about that. If this was an algebraic expression, what could we do? I'm going to put this in red, and I'm just going to put a big caution by it, but we could do something like this. We would sit there and say question mark cancel, right? Can we cancel that? If it was algebraic, we could. Because this is a differential equation and operator notation, that algebraic cancellation really doesn't happen. You've got to be very careful about that. Let me give an example, maybe just a little simpler on that. You could have a signal like this, y equals x. output equals input, no problem. I could have a different system that says dy equals dx. That would have that same idea that if it was algebraic, I could just cancel it, and you'd say those guys are equal, the same system. Well, no, the second system only requires that the derivative of y is the derivative of x. It does not require y equals x. Consider an example of an input x that was equal to a value 3 everywhere, and an output y that was 5 everywhere, right? Both of those have a derivative, a slope of 0, right? The input x slope is 0, and the output y slope is 0. That satisfies this second expression, right? It does not satisfy this first. You can't just go willy-nilly, right, treating these guys as algebraic expressions. You generally can't cancel them. Furthermore, we might add also, right, things like having a derivative and then let's say an antiderivative. I'm going to do that with my operator notation as a 1 over d. You could also do that as a d to the minus 1. These guys generally, so this is what, derivative? This is derivative. This is like an integral or an antiderivative, right? These operators, these ops don't commute, right? In general, taking the derivative of the integral is not exactly the same thing as taking the integral of the derivative. They can be differ by a constant on there. If that seems a little weird or it's a little bit rusty for you, just do a quick review of your calculus in there, and you'll see it. How about if I did an external view of this circuit? So back to this one. We did an internal view. That internal view gave us a first order differential equation. Now if I do an external view on this, and I'm going to make an assumption in here, I'm going to assume that the cap, right, that this capacitor, that the cap is initially discharged. Okay, you build the circuit up, you go grab a capacitor from the shelf in the shop, and sure enough, it shouldn't have a voltage on there. If I look at this guy, this voltage source F, right, it's looking at some load. It goes through a 2 ohm resistor, and then it would split, right? It splits down two sides. What does it see? It sees 2 ohms on this side, and it sees 2 ohms on that side. And then it's followed by another 2 ohms and another 2 ohms. And because this thing was initially discharged, the capacitor in there, it initially had 0 volts on there. What this voltage source F sees is it sees 2 ohms followed by a branch of 4 ohms in parallel with another 4 ohms. It's always balanced. That means the current that goes down this path is going to be the same as the current as that path. And that means the voltage right here is always going to be equal to a voltage there. And that means that capacitor is never going to be seen. This is one of those weird cases, right, where if you have that capacitor initially discharged, it was in 0 state, right? You prodding it from the input side, you would never be able to see that capacitor because the load would always appear balanced and a voltage would never be produced, or it would never be brought onto that capacitor. It couldn't happen on there. So if I look at that from a discharge standpoint, from an external view, from an external view, we never can see that capacitor. And what we see is something that looks more like this. You have an F that's going through a 2 ohm resistor, and then it ends up going into something that looks like this balanced load. And one way, and you can look at the book on this, it goes a half, kind of a half, and a half. That was supposed to be a half on here, and I'll try to give a little context as to where maybe this thing came from, and a half, something like that. This is a very similar kind of circuit as to what you could see externally. Going back up here, I have 2 ohms. Let's do it in a different color. I've got this 2 ohms here, right, with another 2 ohms over there, right? And I've got another 2 ohms over here and a 2 ohm over there. So I know the currents are going to be balanced. If I looked at the overall current that was going through this first resistor, let's call it some I. Because those two paths are balanced, this part here is going to be an I by 2, right? That I by 2 is going to go through a 1 ohm, a 1 ohm, a 1 ohm, and a 1 ohm, something along those lines. So each one of those guys, right, is going to get an equal drop across each one of those 1 ohm resistors by the half of the current. So it ends up looking like those resistors, if you were just looking at it from the output variable V standpoint, they look more like a 1/2 ohm type of resistor that you would see in there. So our plus minus V would be acting on something like that. And if you do the circuit analysis on this, what do you end up getting? You get something that looks like a V equals 1/8 F. The output will always follow the input at just 1/8 strength. You can go through and do a little bit more detailed analysis if you want on that. The external, this is the external, that's the external description, right? The external description on this is not equal to the internal description. And it almost is like in this particular case that the external description went ahead and did that cancellation. And it has to do with the fact that that capacitor is what is called an unobservable configuration in the circuit. So that goes back to that book discussion of unobservable or uncontrollable. Give it a read if you like. What's the end that I want to put into this? We can look at systems from two different standpoints. We can look at it from an internal description or an external description. The internal description is preferred because you can get in there and actually see what's inside the system. You can do all of your full analysis to really figure out what the input-output relationships are and where energy can be stored and what kind of connections there are. They're all explicitly known. External means you can't really see inside, and the only way we can understand the system behavior is by putting some input in and seeing what comes out on the output. An external description is weaker than an internal description, and sometimes it misses stuff. I won't say that it misses stuff a lot. For most of the systems that we'll look at in this class, you won't see this case, or you wouldn't find this condition where you aren't going to be able to see the behaviors inside, because that's pretty rare. This idea of having an uncontrollable or an unobservable system is pretty rare. And so oftentimes our external description, even though it's a little more awkward, comes out being completely in alignment and completely consistent with the internal description. Either way, we should know the difference on them. There is a final topic in this chapter 1, and it's one that I'm not going to spend a lot of time on. I'm going to basically provide just a simple illustration of what it's about. It's really a topic that if you take the controls class, a follow-on class to signals, you would see a lot of this, but in this particular class, it's just a little outside of the context of what we need. Chapter 1 just happens to have a very, very brief introduction to it. And so this is a concept or an idea of something called state space, a state space representation of a system. What is the idea on this? The basic idea of state space is the following. We replace an nth order system, right? We're going to replace an nth order system with n simultaneous first order systems. And use our knowledge of linear algebra to deal with that combination. And we know just how powerful linear algebra can be in being able to understand or represent things. Really, state space is something that was developed kind of in that age of the space race when we were getting ready to put satellites up into space. Satellites and rocketry themselves are complex systems. You might be looking at differential equation models that might be in the 100th of order or even more. And dealing with a 100th order differential equation is hard. It is hard to deal with a single differential equation of a 100th order. Breaking that 100th order differential equation into 100 first order systems has tons of advantages. Turns out the Russians were the first to do this. They were the ones who really came up with the state space representation. And it's a good reason why they were first to space, because it allowed them to more reliably analyze and understand very complex systems. It gave them a systematic framework for doing so. So a very quick example of this might be something like this. Just as a quick example, we won't go too much into detail. I might have something like this. The second derivative of y plus some a1, first derivative of y plus some a2 acting on y being equal to x. This is a second order constant coefficient linear differential equation. I could absolutely analyze this using regular old differential equation knowledge of second order systems. I could also do something like this. I could come up with a variable y1 being equal to y and another variable y2 equaling y dot. These are something called the state variables. And what I can find out then is that y1 dot equals y2 and y2 dot is equal to minus a1y dot minus a2y plus x. This is just using the relationships I have or definitions of y1 and y2 in the original differential equation. You can look through the details later if you want. That's a minus a1 y2 minus a2 y1 plus x. And if I take this whole thing and I express it in a linear algebra style, I can get something like this. I can get y1 dot and y2 dot being equal to, and I'm going to have here a 0, 1 minus a2 minus a1. I'm going to have a y1, y2 plus, and I'm going to have an x here, or 1 times x. And then I'm also going to have in here something like y being equal to, and I'm going to have a 1 and a 0, and I'm going to have a y1 and a y2 plus 0x. And I know I'm putting some zeros in here. I'm just putting it in what is a standard kind of representation for a state space representation. But what you'll notice here, the big important part, is that we have a matrix representation of the system now. And you never see anything in here that's more than a first order derivative. So there's a first order derivative, there's a first order derivative. I had originally had what? We had a second order system. We defined some new variables and we used those variables, carefully chosen variables, to re-express that system, which then could be put into a bunch of matrix representations, the state space representation. And that state space representation, right, we had a second order system. So the big idea here was what? Take a second order system and represent it as a coupled set of first order equations. Second order system, I'm going to need 2 first order equation sets coupled together. And that's what this matrix representation does. What it allows us to do is it allows us to employ linear algebra in order to understand and design and work with these systems, which maybe for a second order system isn't all that big of a deal, but when you get to super high order systems or larger or higher order systems, it is a big deal and it really helps out. We are not going to use this a bunch, so I might give one homework problem just to kind of give you some incentive to look at it, but you won't be held responsible for doing state space stuff on an exam. So that concludes out chapter 1. Next time we're going to go into chapter 2, which is all about solving constant coefficient linear differential equations using time domain methods.